According to power quality experts, while lightning is the most common source of failed equipment, TOVs and sustained overvoltage events will be the most destructive power quality events over the next 10 years. So how can you protect against TOVs and sustained overvoltage events? You might install a UPS system at a cost of $100,000 and upwards, or you might try a voltage regulator, but they're large and use fairly old technology. Or you could try the catastrophic protection system from current technology. CAPS uses a combination of MOVs with selenium cells to provide an effective strategy against transient surges and temporary overvoltage events. The MOVs handle high voltages of a very short duration. The selenium has a slightly slower response time, but can provide protection against lower overvoltage conditions that last longer. The MOV is the sprinter, the selenium is the marathon runner. By combining MOVs and selenium cells in a hybrid protection system, CAPS provides protection from power quality events from multiple cycles up to seconds, significantly longer than any MOV-based protection devices. This seemingly small amount of time is like an eternity to equipment loads when they're stressed by power quality events. CAPS protects against transient surges and also effectively diverts to ground the dangerous currents caused by TOV events. We'll demonstrate how in our next segment. This demonstration is very similar to the previous one, except for one difference. In this test, we'll add a selenium cell in parallel with the MOV. Our current transformers are set up to detect current flow through both devices. The current levels will be displayed on this monitor. We'll begin the test by subjecting the MOV in the selenium cell to a 30-cycle TOV at 150 volts. And we can see that neither the selenium nor the MOV did any clamping at that voltage. The downstream equipment would see the full extent of that power quality event. Now we'll increase it to 170 volts. And as we can see on the monitor, there was no current flow through the MOV. It did not clamp and provided no protection at this voltage. However, the selenium cell has begun to clamp. It is now providing protection to both the MOV as well as the downstream equipment. Now I'll just reset the scope. We'll now increase the voltage to 200 volts. At 200 volts, we can see that the selenium cell is still providing protection with 16.4 amps flowing through it. Let me reset the scope. We'll now increase the voltage to 220 volts. During our MOV-only test, this was the first voltage level where the MOV began to provide protection. With the selenium cell in the circuit, the MOV did not provide any protection during the event, but the selenium cell did, with 24.8 amps flowing through it. I'll reset the scope. Now we'll increase the voltage to 240 volts. Remember that during an MOV-only test, this was the voltage level that caused the MOV to fail. As you can see, the MOV is still intact and has no current activity because the selenium cell is providing all the protection during the TOV event. At 240 volts, the selenium had 32 amps flowing through it. Now I'll reset the scope before the next test. We'll now increase the voltage to 270 volts. 270 volts is well past the voltage level that caused the MOV to fail. As you can see, the MOV is still intact and has very little current activity. The selenium cell had 39.2 amps flow through it and has continued to protect the MOV and the protected load during the TOV event. Now I'll reset the scope before the next test. Let's leave the voltage right here at 270 volts and remove the selenium cell from the circuit. What do you think will happen when the MOV is subjected to a 270 volt event without the selenium cell? As you can see, when the MOV is subjected to the 270-volt TOV event without the selenium cell in the circuit to protect it, it fails. So you can clearly see that MOVs are not capable of surviving TOV events because as the voltage increases, the clamping current through the MOV increases, and it can't dissipate the heat fast enough. But CAPS provides optimum protection because the selenium provides a higher clamping current capacity and a larger thermal mass to dissipate heat. The selenium cell also has a lower clamping level, so it can provide protection against TOVs that the MOV doesn't even see. In our next segment, we'll talk about the best way to install SPDs. Now that we've seen what a good surge protection system can do to protect your equipment, the question arises, should an SPD be internally mounted or externally mounted with your electrical system? We've designed CAPS as an external system because we believe an external system provides better and safer performance at a lower cost. Up to now, most SPDs have been designed as internally mounted systems, but IEEE's Emerald Book Standard 1100 states that integrated SPDs are not recommended because they greatly increase the risk of collateral damage caused by product failure and arc flashes. Internally mounted SPDs force employees to work on live gear, greatly increasing personal risk. Live parts are exposed every time a part is replaced or maintained. You either have to shut down or suit up. Secondly, internally mounted SPDs may cost less to install initially, but will result in higher replacement costs associated with replacing protection modules, alarm boards, alarm sensors, or any other failure of an internally mounted system. The switchgear and panel companies say that the integrated product is the best solution because they have tens of thousands of their products already installed, and they don't want to admit to a bad idea. But even they are aware of the problem, and they're now de-emphasizing the integrated option. Their new product rollouts are focusing on the external solution. There are a couple of other issues regarding product design that we think you should be aware of. UL 1449, an underwriter's laboratory document dealing with the safety of SPDs, has undergone some recent revisions. UL 1449 second edition, which became effective in 2007, primarily focuses on ensuring SPDs fail in a safe manner. All products were subjected to 2 new tests, an expanded overvoltage test and an application of 4 different limited currents to ensure that the unit under test either stabilized its temperature safely or that it took itself offline safely by blowing some sort of fuse or tripping a breaker. UL 1449 states that all SPDs must be designed so that the SPD fails safely. It must have a mechanism that takes the SPD safely offline before the MOVs fail. As a consequence, other SPD manufacturers that use only MOVs have designed their products so that they're now less robust than they were. They're taken offline sooner, which makes them safer, but the SPD is no longer protecting the electrical system. CAPS, with its hybrid selenium design, stays online much longer, protecting your system longer. UL 1449 3rd edition, which becomes effective September 29, 2009, creates 4 categories of SPDs. Current technology's catastrophic protection system already meets these standards as a Type 1 SPD. UL 1449 3rd edition also establishes a new test to ensure product integrity by stressing the SPD to determine whether any significant amount of degradation will occur. This is called the nominal discharge current test, and it stresses the SPD with a total of 15 transients in 3 phases, at a nominal discharge current selected by the manufacturer. The voltage protection rating is measured before and after the test, and the results must not vary by more than 10%. Another issue you should know about concerns NEMA LS1, a standard published by the National Electrical Manufacturers Association concerning SPDs. You should know that some manufacturers have voted to reduce the standards of NEMA LS1, to no longer require a surge test that will prove a unit's ability to handle the claimed single surge rating. Why? Perhaps it's because their products can no longer meet the single surge rating they claim for their products. They merely want to base their products' ratings on the number of MOVs their system has, instead of industry standard performance results per NEMA LS1. Current technology was among only a handful of manufacturers that voted against lowering the standard. Remember, not all overvoltage events are created equal. Temporary overvoltage or sustained overvoltage events can be just as destructive as a lightning strike. MOVs are great for transient surge protection, but TOVs and sustained overvoltage events can and do happen in the real world. And a better TOV solution is available. CAPS, the Catastrophic Protection System, from Current Technology.